Hello friends, in previous lecture we have studied properties of congruence modulo in relation. With help of that, or we'll see now applications of that properties in as examples. So take the first example. Show that 41 divides 2 raised to 20 minus 1. 2 raised to 20 minus 1, or 2 raised to 20 is congruent to 1 mod n, 1 mod 41, or so that find a so that 1 is the remainder, when 2 raised to 20 is divided by 41. If we divide 2 raised to 20, then the remainder should be 41. So solution. 2 raised to 20. So I will select the number power of 2 in such a way that which is closer to 41. So 32 is near to 41, and then I can find a remainder when 32 is divided by 41. It may be positive or negative. Okay. So here 32, here 41 divides 32 minus plus minus 9 is equal to 41. Therefore 32 is congruent to minus 9 modulo 41. That is, and this is power of 2 raised to 5 is congruent to minus 9 modulo 41. Right. Now, if I take its square, therefore 2 raised to 5 its square is congruent to minus 9 its square modulo 41, which is nothing but 2 raised to 10 is congruent to 81 modulo 41. Okay. Now 81 is congruent to minus 1 mod 41, as 81 divides or 41 divides 81 minus 1 is equal to 82. Therefore 81 is congruent. Yes, 81 is congruent to this. So this is 1, this is 2, from 1 to and transitivity. 1, 2 and transitivity. 2 raised to 10 is congruent to minus 1 mod 41. Therefore 2 raised to 10 its square is congruent to minus 1 square modulo 41. We know that if A is congruent to B mod n, A is congruent to B mod n implies A raised to k is congruent to B raised to k modulo n. So by using this property we will get this, and therefore 2 raised to 20 is congruent to 1 mod 41. Is it clear? Now we have one property. If A is congruent to B mod n, then A and B leaves same remainder when divided by n. Okay. If A is congruent to B mod n, then A and B leaves same remainder when divided by n. This implies and here if we divide 1 by 41, okay, here if 1 is divided by 41, then 1 is equal to 0 times 41 plus 1 implies 1 is remainder when 1 is divided by 41. And therefore 2 raised to 20 divided by 41 leaves the remainder 1. Remainder 1. Is it clear? So here I have not proved this property. We have to prove it. We have to prove that property. So immediately we will prove that property now. So we will take it as theorem. There is also one application of congruence modulo n relation. Okay. Theorem. For n greater than 1, if A is congruent to B mod n, for AB belongs to Z, then A and B leaves same remainder, A and B leaves same remainder when A and B are divided by n. Now since A is congruent to B mod n implies n defiles A minus B, and therefore A minus B is equal to nk. For some k belongs to Z. 1. Now applying division algorithm to B and n, there exists QR belongs to Z such that B is equal to NQ plus r, where 0 less than equal to r less than n. Is it clear? So, this is 2. From 1, A is equal to B plus Nk, and therefore A equal to, what is B? Nq plus R plus Nk. From 2, and which is equal to n times q plus k r, which is equal to nq dash plus r, where 0 less equal r less than n. From 2 and 3, from 2 and 3, r is the remainder, r is the remainder, r is the remainder when a and b are divided by n. Thus, if A is congruent to B mod n, then A and B leave same remainder. Thus, if A is congruent to B mod n, then A and B leave same remainder, when A and B are divided by n. Is it clear? Next example, find the remainder when 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus dot etc. up to n factorial, n greater than 4 is divided by 24, whatever the n may be. Solution: for k greater equal 4, k factorial is equal to 1 into 2 into 3 into 4 into dot up to k is divisible by 4. Therefore, 4 factorial plus 5 factorial plus 6 factorial and so on n factorial is divisible by 4 for divisible by 4. For any n greater equal 4. Therefore, 4 factorial plus 5 factorial plus dot dot etc. up to plus n factorial is congruent to 0 mod n 1. Okay. Now 1 factorial plus 2 factorial plus 3 factorial, which is nothing but 1 plus 2 factorial is 2, 3 factorial is 2 into 3, that is 6. 6 plus 2, 8 plus 1, 9 is congruent to 9 mod 4. Okay. So here what is the reason? A congruent to B mod n, C congruent to D mod n implies A plus C is congruent to, or since if n divides A, n divides B implies n divides A plus B. So 4 divides each k factorial for k greater equal to 4. So 4 divides 4 factorial, 4 divides 5 factorial, so 4 divides 6 factorial and so on. 4 divides addition of them also. Again, by property of now congruence modulo n relation, from 1 to 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus dot dot etc. up to plus n factorial is congruent to 0 plus 9 modulo n. Since A congruent to B mod n, C congruent to D mod n implies A plus C is congruent to B plus D mod n. Right? And therefore 1 factorial plus 2 factorial plus dot dot up to n factorial is congruent to 4 9 modulo n, 9 modulo 4. Now if 1 is the remainder, or 9 is equal to 4 into 2 plus 1, okay, implies 1 is the remainder when 9 is divided by 4. So this is 3, this is 4, from 3, 4 and result. We know for n greater than 1, if A is congruent to B mod n, this is your 5. So from 3, 4, 5, from 3, 4, 5, 1 is the remainder. 1 is the remainder when 1 factorial plus 2 factorial plus 3 factorial plus dot dot up to n factorial, n greater equal 4 is divided by 4. Sorry, here 24. Is divisible by 24. Replace 4 by 24 everywhere. Sorry. 24. Okay. (24). Here 24. Question is 24. So we have to take 24. So now 9 is remainder when 9 is divided by 24. Okay, 9 is equal to 24 into 0 plus 9. Okay, so 9 is the remainder when this is divisible by 24. Is divided by 24. Okay. So with this discussion, we'll stop our session here. Thanks for listening lecture carefully. Bye bye.